So Chapter 7 deals with atomic structure and periodicity. And we're going to take a look at this chapter section by section. We'll start with electromagnetic radiation. This is pretty much a review of what you learned about EM in Honors Chem. So we'll start with the basic idea of what we're talking about. Electromagnetic radiation is a form of energy. It acts as a wave as it travels. And it includes all sorts of types of energy that all fit under this umbrella. Visible light, so what you can see, X-rays, ultraviolet, infrared light, microwaves, radio waves, cosmic rays, gamma radiation. All of these things are not are traditionally thought of as particles, as mass, but as energy. The speed of all of these types of energy is the speed of light, which is 2.9979 times 10 to the 8th meters per second in a vacuum. Usually we round that to 3.00 times 10 to the 8th meters per second. Yes, it's different if you're traveling through a medium like air or water. The speed changes, and that accounts for some rather interesting properties of electromagnetic radiation and some of the phenomena that we witness in our atmosphere, for example. When we put all these together, we can arrange them according to several properties to form something called the electromagnetic spectrum. This should be very familiar to you. You've used it before, and it simply shows you, in this case, breaks down the types of electromagnetic radiation by wavelength. Okay, but we can do this certainly by energy or by frequency, any of the properties that we're familiar with. What's important to note, and something that you need to remember, is the visible light spectrum. Specifically, the wavelengths of the visible light spectrum are from 4.00 times 10 to the minus 7 to 7.00 times 10 to the 7th meters. Another way of saying that would be 400 to 700 nanometers, since a nanometer is 10 to the minus 9th meters. You can do the calculation or the conversion on your own to prove that. So some of the properties that we need to become familiar with. Wavelength. Okay. Represented by the Greek letter lambda, which is lowercase l, and it's the distance between points on adjacent waves, the same point on two waves that are right next to each other. Typically, we report this in nanometers, especially when we're dealing with visible light or shorter wavelengths. It's simply easier. It's easier to say, for example, 700 nanometers rather than 7.00 times 10 to the minus 7th meters. So you need to be familiar with the conversion between meters and nanometers. The other property that we're interested in is frequency. Frequency is represented by the Greek letter ni. It is not pronounced nu, it is pronounced ni. Although mostly everybody in this country, all the Americans, say nu. I have it on good authority from a native Greek speaker that it's not pronounced nu, it's pronounced ni. Anyway, the definition of frequency is the number of waves that pass a point in 1 second. Okay? Since we're talking about the number of waves per second, then the unit for frequency is actually 1 over seconds, or seconds to the minus 1. That was determined by a physicist by the name of Hertz, and so we often use his name as the unit. So 1 over seconds, or seconds to the minus 1, or cycles per second, or waves per second, or Hertz. Take your pick. They're all used. And wavelength and frequency are inversely proportional. So they're inversely proportional by a constant, and it happens that that constant is the speed of light. So c in this formula represents the speed of light, lambda is the wavelength, and ni is the frequency, and this is mathematically how you represent an inversely proportional relationship. You multiply the two values together that are inversely proportional, and they always come out to be the same value, constant. That means if one goes up, the other has to go down in order to keep the product the same. Make sense? So here's just a look at how the wavelength-frequency relationship works. Wavelength lambda is, of course, the distance between the same point on two adjacent waves. Usually it's wave top to wave top, but it doesn't have to be. So this top wave, this red wave here, has a frequency of 4 cycles per second. 1 second is the width of that top line, and the wave cycles completely 4 times in that 1 second. And we have this wavelength. If we make the frequency twice as big, in other words, we put 8 wavelengths, 8 waves into that 1 second, then the wavelength gets smaller. As a matter of fact, it gets smaller by exactly a half. And similarly, if we double again the frequency, the wavelength again gets cut in half. So that's the relationship. That's how it works. The second section here talks about the nature of matter. And so let's take a look at historically what we used to think of it. And as a matter of fact, many science classes still teach it this way. But it's really an old way of looking at things. Matter and energy are distinct processes in the old way. Matter had mass, it had position, it was made of particles. Energy was made of waves, it had no mass. It was delocalized, meaning you couldn't really pinpoint where it was. You could just sort of see the effects of it, or you could follow the transmission of a wave. Up to the beginning of the 20th century, this was how things were viewed. And it's a simple way of looking at things, which is why it's still taught in a lot of classrooms today. But around the turn of the century, Max Planck, who was German, figured out through some mathematical calculations and some experiments that he began to believe that an object will emit energy in small packets. And those packets were called quanta. So a quantum, singular, quanta, plural, is the minimum amount of energy that can be gained or lost by an atom. So atoms gain or lose energy in the smallest piece, the smallest packet that they can gain or lose is called a quantum. So he came up with this general relationship that the change in energy of an atom can be represented by n times h times ni. That's frequency again, where n is the number of atoms in this case. So the more atoms you have, the more energy you're going to have. That n is often lost when you're talking about these things, but it's kind of important when we're starting to talk about the energy of these packets of radioactivity or of electromagnetic radiation, because the more atoms you have, the more energy you have. So yes, it may seem like a small amount of energy, but if you have hundreds of billions of atoms doing this at the same time, you're talking about quite a bit. Planck's constant is the h in this equation, and mathematically it was determined to be 6.626 times 10 to the negative 34th joules times seconds. The units are going to be useful in canceling out, for example, hertz, which is 1 over seconds. So then we got this guy. You all recognize Albert Einstein, I hope, by now. Brilliant physicist. And it was Einstein's work that actually began the paradigm shift in understanding the nature of matter and energy. Einstein basically said we can't really think of these two things, energy and mass and matter, as being separate. That in fact energy is made of particles. These particles he called photons, which comes from the Greek word photos, or light. Since we know, according to Planck's constant, the energy per photon is h times ni, and since ni is equivalent to c over lambda, we can put them together and get hc over lambda. So we can actually figure out, based on the wavelength of energy, how much energy each particle will have. The other thing that Einstein is very famous for is showing that energy and mass are essentially the same thing. The difference is that mass has the speed of light involved in it. So as you increase the speed of matter, it becomes more energy-like. There's a lot more to this, and there's an entire area of physics called quantum mechanics and quantum physics that's dedicated to studying this. We don't need to get too far into it, but we just want to understand that the way we think about matter and energy now is very different. Okay, so to sort of look at what we're doing here, here is the original representation of wavelength and frequency inversely proportional, which we can rearrange to solve for frequency. So frequency is equal to c over lambda. We can take Planck's work, E equals h times frequency, and we can combine the two of them together to make this, E equals hc over lambda. Okay? Now, take Einstein's other idea, that energy and mass are essentially the same, and let's put those two together, replacing E with mc squared. So we get hc over lambda equals mc squared. Now we're going to do a little bit of algebra, and we're going to rearrange this such that lambda is by itself. When you do this, you end up with a slight variation on this theme. It's h over m, which is mass, times v. Now this is not ni, this is not frequency, this is v, velocity. So look at what the implications of this formula are. anything that has mass and velocity has a wavelength. Now, it may not be perceptible to you, but when you walk down a hallway, you have a wavelength. It's a very, very long wavelength. So it's not going to be able to be picked up by any kind of instrumentation that we have, but that's what Einstein was saying. Matter and energy are essentially the same thing. We continue on in the 1920s. A French physicist by the name of Louis de Broglie said, okay, we have on one hand the old way of looking at things, matter as particles and energy as waves, and on the other hand we're starting to see that matter is sort of has the same properties of energy, just what's different about them is how fast the particles are moving. De Broglie went a little further and said, you know what? Matter and energy, being that they're the same, have to have both particle-like and wave-like characteristics. This is called the wave-particle duality. So when you're thinking about matter in terms of waves, you're looking at things like frequency and wavelength. But when you're thinking about it in terms of particles, you're looking at things like mass and velocity. And what's interesting about this, and what really sort of bakes your noodle a little bit, is that they're both at the same time. It's called the wave-particle duality. And matter has both of these properties, and so does energy, since they're the same, at all times. It's just what you happen to be looking for is what you'll see. It's a very strange thing. So the main ideas that we want to talk about then in this video is that matter and energy are not distinct. They're actually the very same thing. Energy is just a form of matter. Larger objects, things with lots of mass, they mostly behave like particles. Things with very, very small mass, like electrons, are mostly wave-like. And this is the key to understanding the distinction between Bohr's model of the atom, where the electrons orbited around the nucleus like planets, and the new model of the atom, where electrons are actually like waves. And it's because they're small. Electrons are so small, their mass is so small, that their behavior is more like a wave than like a particle, even though they're matter. They have mass. Okay? Lots of stuff in this video. Not a whole lot to do, just some basic concepts. Make sure you stop, rewind, take good notes, and we'll move on.